The fundamental theorem for divergences. The fundamental theorem for divergences states that volume integral del dot v d dou is equal to surface integral v dot dA over a closed surface. Of its great importance, this theorem has special names: Gauss's divergence theorem, Green's theorem, or simply the divergence theorem. Like the other fundamental theorems, it says that the integral of a derivative, in this case the divergence, over a region, in this case a volume, is equal to the value of the function at the boundary, in this case the surface that bounds the volume. Notice that the boundary term is itself an integral, specifically a surface integral. This is reasonable. The boundary of a line is just two endpoints, but the boundary of a volume is a closed surface. Now, the geometrical interpretation of divergence theorem. If V represents the flow of an incompressible fluid, then the flux of V, the right hand side of this equation, is the total amount of the fluid passing out through the surface per unit time. Once again, if V represents the flow of an incompressible fluid, then the flux of V is the total amount of fluid passing out through the surface per unit time. Now, the divergence measures the spreading out of the vectors from a point. A place of high divergence is like a faucet pouring out liquid. If we have lots of faucets in a region filled with incompressible fluid, an equal amount of liquid will be forced out through the boundaries of the region. In fact, there are two ways we could determine how much is being produced. One, we could count up all the faucets, recording how much each puts out. Or we could go around the boundary measuring the flow out at each point and add it all up. You get the same answer either way. That is, integral faucets within the volume is equal to integral flow out through the closed surface. This is in essence is what the divergence theorem says. The fundamental theorem for curls, which goes by the special name of Stoke's theorem, states that surface integral del cross V dot dA is equal to integral V dot dl over a closed path. As always, the integral of a derivative, here the curl, over a region, here a patch of surface, is equal to the value of the function at the boundary, here the perimeter of the patch. As in the case of the divergence theorem, the boundary term is itself an integral, specifically a closed line integral. Now, the geometrical interpretation of Stoke's theorem. You can recall that curl measures the twist of the vectors V. A region of high curl is a whirlpool from our previous lecture. If you put a tiny paddle wheel there, it will rotate. I'll say once again, curl measures the twist of the vectors V. A region of high curl is a whirlpool, and if you put a tiny paddle wheel there, it will rotate. Now the integral of the curl over some surface, or more precisely, the flux of the curl through that surface, represents the total amount of swirl. And we can determine that swirl just as well by going around the edge and finding how much the flow is following the boundary, as in figure. You may find this is a rather forced interpretation of Stoke's theorem, but it's a helpful mnemonic, if nothing else. You might have noticed an apparent ambiguity in Stoke's theorem concerning the boundary line integral. Which way are we supposed to go around, clockwise or counterclockwise? If we go around the wrong way, we will pick up an overall sign error. The answer is that it doesn't matter which way you go as long as you are consistent. For there is a compensating sign ambiguity in the surface integral. Which way does dA point? For a closed surface, as in the Divergence Theorem, dA points in the direction of the outward normal. But for an open surface, which way is out? Consistency in Stoke's theorem, as in all such matters, is given by the right-hand rule. If your fingers point in the direction of the line integral, then your thumb fixes the direction of dA, like this. Now there are plenty of surfaces, like infinitely many, that share any given boundary line. Twist a paperclip into a loop and dip in soapy water. The soap film constitutes a surface called as the soap film. The wire loop has its boundary. If you blow on it, the soap film will expand, making a larger surface with the same boundary. Ordinarily, a flux integral depends critically on what surface you integrate over. But evidently, this is not the case with curls. For Stoke's curl theorem says integral del cross v dot dA is equal to the line integral of v around the boundary, and the latter makes no reference to the specific surface you choose. From this, you can say corollary 1, integral del cross v dot dA depends only on the boundary line, not on the particular surface used. Once again, integral del cross v dot dA depends only on the boundary line, not on the particular surface used. And corollary 2, integral del cross v dot dA over a closed surface is equal to 0. Since the boundary line, like the mouth of a balloon, shrinks down to a point, and hence the right side of this equation vanishes. These corollaries are analogous to those for the gradient theorem,